Başlayabiliriz.
Hello everyone, my name is ismail, and I'm going to present you today the paper written by John Key Osterhout, Why Aren't Operating Systems Getting Faster as Hardware? This is a conference paper in 1990. As an introduction, the initial goal of the osterhout is comparison between Sprite, which is at that time he employed in Berkeley. The Sprite is a Unix-based operating systems for research, for experimental purposes in Berkeley, and he's going to make a comparison between Sprite and the vendor-supported Unix derivatives on similar hardware. But he noticed that the fast machines, fast processors at that time does not seem as fast as the hardware when he ran the operating systems on that machine. And he also noticed that there is two factors of poor OS performance, and that hardware, first the memory bandwidth, and the disk IO. And there is also a problem in file systems. Unix need memory IO before key operations. We will see in benchmarks why I wrote this in here. This is the hardware using the experiment. When he does the experiment, this is MIPS M200 2000, and there is two processor architecture in this hardware. There is RISC and CISC, and there is, you can see there is a MIPS rating in this table. We compare, when he doing the research, he compares the performance of the benchmark with this MIPS ratings of the processors. And when he doing the benchmarks, he end up the benchmarks with memory. There is enough memory in every benchmark. No significant paging in EO-based, EO-intensive benchmarks. Files fit in main memory buffer caches when he doing the read and writes. Read and write benchmark. The machine varies, but he mentioned that the machine varies in the disk configurations, and he always used the same disk system in particular machines except the Maclean DS3100. And the operating systems, there are 6 operating systems when we doing the experiment. The Ultrix, it's a DA product of a derivative of the Berkeley 3.4.3 BSD Unix, and also the Sun is Berkeley Sun derivative. And he also used RISC OS, it's a MIPS computer systems OS for M200 and 2000. HPUX, the Hamlet Packets Unix product. Mac, a Unix-like OS developed by Carnegie Mellon. And Sprite, the first I mentioned in the initial, is an experimental OS developed by the Berkeley. The first benchmark is the kernel entry exit. When he doing the experiment, he always he repeatedly invokes the get pit, which is the getting the process ID, and he gets this table from these configurations. as you can see, when I come back to hardware, the the Sun 375 microwatts 2 and the BIL601 800, there are 6 CISC configurations, and in this table it shows that the risks are faster than the CISC ones, but this is not enough. This is not fast enough because it scales only from 0.5 to 0.8. The context switching benchmark, when he does the experiment, he repeatedly operates the S-switch operator, and he repeatedly forking a child and make a memory switch between child and the parent processes. The measurements of this table made by 2 context switches and 1 write kernel operation and 1 read kernel operation, and we get this by this operation, by this benchmark, that risks are faster again, but it's now scaled from 0.2, 0.3 from 0.5. The third benchmark is the select. It exercises the select kernel call by creating pipes with data. It creates pipes and it fills some pipes with data, and he tries to hit that pipes with data, and he tries to determine that how many pipes that are readable when he uses the select operation, and he sees that the commercial OS is which is Sun OS, Ultrix, and RISC OS is better than the others, the experimental ones and the Ultrix and the other one. And he also observes that the RISC OS select kernel call is faulty. This is an observation because if the pipe is empty, it takes a little time, but if pipes with data, it waits 10 microseconds to process this pipe. And this is the table he gets when we're doing this experiment. Again, the DS. This is the fourth benchmark. It's the block copy. It's copies a block of data from one memory point to another memory point, and by using the bcopy kernel operation, it uses 2 types of blocks of data. First, the size of a cache to make data to take place at the memory caches, which is utilizes the CPU most efficient. And second one is to larger than the cache to catch the cache misses. And at this point, CISC's machines are better than the RISC's. And in this benchmark, he observes that the more processor speed in the RISC machines, the less performance for memory copying. This architecture is not good at memory copying, memory operations. And this is the table. As you can see, these machines getting good results by comparing the MIPS values. This is the 5th benchmark, and this is read from the file cache. In this benchmark, he opens it. Opens a page, and then he writes and reads from this page definitely 16K kilobytes of data,
And all the files he uses in this experiment, size of a memory cache again, memory buffer cache. You can see from the table that again this RACS architectures are not good in memory. This is the only macro benchmark in this paper. The Andrews, modified Andrews benchmark is developed by the Satyanarayana, I can't spell that, for measuring the performance of the APS. Now, in this benchmark, it operates copying a file of file hierarchy, which has a source code, includes a source code in it, and then give every file a new hierarchy, then process these files, and occasionally, last time he compiles the source code. There's, he mentioned that in original Andrews benchmark, every machine has different C compiler, but in this experiment we always use GNU C compiler. And two operations to observe. First is copy, and the second one is the compile, and two configurations for the memory operations. First is local, and the second is remote. From a, he reads files from a network. This is the table of the readings. How many seconds a configuration takes place, took to read, copy and compile. And this one is the ratings of the configurations. Which one is that? Yes. The Sprite DS3100 is the best one for the rating. He mentioned that this one, the DS300 Sprite, is the best in remote, and he cannot figure out why it is. And he's going to take two other experiments to prove or observe why this happens. And this is the first one. Results. The benchmark results shows that the faster machines have small MIPS relative speeds than slower ones. And Sprite is the fastest exact Mac on Sun 4, which shows us that the local it's 10 to 20, and in the remote it's 30 to 70. The NFS file system is not good, it's remote, and its penalty increases when the CPU speed increases. And this is the observation. The S300 Ultrix local is slower than expected. Same anomaly he observes. And this is the first operation we tried to understand why this Sprite is better in remote. This is the first one. It opens and closes repeatedly a file. It sees that when he doing the open and close operations, the Unix derivatives are faster than the Sprite. It contradicts with the Andrew benchmark's result. Measurement in server, it takes measurements in the server communication time when we see the table, and because these Unix derivatives are faster than Sprite, because Sprite communicates in every operation. He communicates with the server when he tries to open or close a file in the server, NFS occasionally communicates. It's need to check if file exists once a while. And NFS never communicates because he waits to check from the server to files exist. He never checks files exist or not. And this is a table, the MIPS relative speeds. There is two types of file. There is a one element foo and the four elements ABC foo. And you cannot see that why sprite is good in remote. Then we doing the other experiment. This one, create and delete. Again, in local or remote, he tries to create, use, and delete a temporary file, and it shows that why sprite is good in remote operations, because in sprite, if a temporary file to exist and flash to the memory, because when he leaves at least 30 seconds, if it is not, he going to delete it. He's going to be deleted. And Unix derivatives always need to flash to the memory when you try to create, delete, or read from the memory. And this is the table. And there is a sprite. You can see that sprite remote is 1.5. It's very good. The conclusion of this experiment is see four potential problem areas, two for the hardware designers, the CPU designers. First, the memory bandwidth, and the second one is the context switching. And two for the OS developers. First, decoupling file system performance from disk performance. And we give two suggestions. First, the non-volatile type buffer between main memory and disk, and the second one is log structured file systems. And the second one of the problem is network protocols, because he affects the remote operations. Thank you for listening.
Okay. Is there any question?
Ne sorar? Şeyi sorar. Şuradakini neyi sorar? Aynen. Problemler ne? Gördüm.